morning to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering. And today my content is GTU question paper solution of the subject of vector calculus and linear algebra of December 2013. So up to question number 4 we already seen this question paper. So let's see question number 5. Question 5a, first part. Let W be the space of P3 spanned by the vectors V1 equal to 1, 4, 5, 6, 9. So this is a vector of R5, V2 that is equal to 3, minus 2, 1, 4, minus 1, V3 that is equal to minus 1, 0, minus 1, minus 2, minus 1, and V4 that is equal to 2, 3, 5, 7, 8. Find the basis for the orthogonal complement of W. This question was asking 5 marks. The space W spanned by V1, V2, V3, V4 is the same as the row space of the matrix. So first of all, just try to understand how we solve this question. Here we have W, we have space spanned by P3, space of P3, P5, sorry, spanned by P5 by the vectors V1, V2, V3, V4, right? These all are vectors of R5. Okay, so how to solve this question? First of all, we have to convert using that V1, V2, V3, V4. We use matrix, right? This matrix. Now then convert this matrix into a row echelon form, and using that solution of the matrix we can find the basis for the orthogonal complement of W. So the space W spanned by V1, V2, V3, V4 is the same as row space of the matrix, right? So this is A. A is a 4 cross 5 matrix where the first row is exactly the V1. You can see 1, 4, 5, 6, 9. So this is first row 1, 4, 5, 6, 9. This is second row 3, minus 2, 1, 4, minus 1. This is third row minus 1, 0, minus 1, minus 2, minus 1, and the fourth row is 2, 3, 5, 7, 8. So next target is we have to convert this matrix into a row echelon form. And how we convert any matrix into a row echelon form? So there are some conditions to become a row echelon form. The first condition is if there is any zero row. If there is any zero row, it should be the bottom of the matrix. The second condition is in any column, if there is any leading entry of that row of the row, then below that leading entry all the elements should be 0. And whenever we are going from above to below in the matrix, our leading entry definitely is going from left to right, right? So if these three conditions are satisfied, then we can say that a matrix is in row echelon form. So you can see this matrix is not in row echelon form. So definitely we have to convert this matrix into a row echelon form. So consider this first row. What is our leading entry? This one leading entry, or sometimes we call pivot, is first non-zero element in any row, that is called leading entry, right? Whenever we are going from left to right, whatever the first non-zero element, that is our leading entry. So this is our non-zero element 1. So this is our leading entry. I want make 0 here in that column. Below that leading entry, everywhere I want 0 here, right? So instead of 3 I want 0 here, instead of minus 1, and instead of 2. So what we have to do, using some row operations, you can definitely make these 3 elements become 0. So the first process is what we have to do. The first process to become a row echelon form of this matrix, we have to multiply first row with minus 3 and add into the second row, and we multiply first row with 1 and add into the third row, and then multiply first row with minus 2 and add into the fourth row, right? So three row operations we are doing together. So first we have to multiply first row definitely as it is, and then we multiply first row with -3 and add into the second row. So what second row become 0, right? 3 minus 3 0. This is -2 minus 12, so that is -14, and this is 1 minus 15, so that is -14, right? So you can see 0 minus 14, then 4 minus 18, okay, 4 minus 3 into 6, so that is 18. So 4 minus 18, that is also -14, and -1 minus 9 into 3, so that is -27. So -1 minus 27, that is -28. Okay, now next process is we multiply first row with 1 and add into the third row. So definitely just we have to add this first and third row, and right, so and put all the values in the third row. So 1 minus 1 0, this is 4 plus 0 4, this is 5 minus 1 4, 6 minus 2 4, 9 minus 1 8. Okay, so this is 0 4 4 4 8. Then multiply first row with -2 and add into the fourth row. So 2 minus 2, that is 0, 3 minus 2 minus 2, that is 0, then 3 minus 4 into 2 8, so 3 minus 8, that is -5, 5 minus 2 into 5, so that is 5 minus 10, so that is -5. Okay, and then 7 minus 12, that is -5, and then 8 minus 18. Okay, 8 minus 2 into 9, so that is 18. So 8 minus 18 minus 10. So this fourth row become 0 minus 5 minus 5 minus 5 minus 10. Right, now you can see this is our leading entry. In the first row, this is our leading entry. Below that leading entry, all the elements now we have 0. Now take second row. So in second row I want here 1, right? So that's why we multiply second row with -1 by 14. Similarly we are multiplying third row with 1 by 4 and multiplying fourth row with -1 by 5. Okay, so the first row is as it is, the second row become 0 1 1 1 2, right? Similarly you can see the third and fourth row are same, 0 1 1 1 2, and the fourth row that is also 0 1 1 1 2. Now it's quite easy to understand that in second row this is our leading entry, second, third and fourth row, all of them are same elements, right? So whenever we are multiplying second row with -1 and add into the third and fourth row, the third and fourth row become 0 row, right? So exactly that are our next processes. We are multiplying second row with minus, okay, we are multiplying second row with -1 and add into the third row, and multiplying second row with -1 add into the fourth row. So this third and fourth row become 0, first and second row are as it is, right? So this is not a process, okay, we are doing here. So just cancel this one, this process. Okay, now how many non-zero row? Only 2 non-zero row, right? So the last matrix is in row echelon form. Definitely we want to solve this equations. So the number of non-zero row in this matrix is 2, hence the rank of the matrix is 2, and there are 5 minus 2. How many column we have? 5 columns, right? So 5 minus 2, that is equal to 3. So that means 3 are free variables, right? 3 are free variables, or in other words, the nullity of the matrix, right, is equal to 3. So now exactly what variables we have to suppose see we have to take three variables are free variables, but what are that 3 variables? The first column is x1, second column is x2, third column is x3, fourth column is x4, and fifth column is x5, right? Now in which column we don't have any leading entry? See, the first column we have leading entry, the second column this is our leading entry, but the third, fourth and fifth column we don't have any leading entry, right? Third, fourth and fifth column we don't have any leading entry. So that's why we have to take x3 is equal to x3, x4 and x5. That three variables are free variables, right? Because of third, fourth and fifth column we don't have any leading entry in this row echelon form matrix. So that's why we are taking x3, x4 and x5 are free variables. So x3, x4 and x5 are free variables, and we take x3 is equal to s, x4 is equal to t and x5 is equal to u. So the null space of A is the solution space of the homogeneous system Ax is equal to 0, right? And that is exactly the orthogonal complement of W. Now don't forget what is our question. See, find the basis for the orthogonal complement of W, right? And W is what? Spanned by this 4 vectors, space of P5 spanned by this 4 vectors, and we want to find the orthogonal complement of W. So whenever we want to find orthogonal complement of this type of space, what we have to do? That is the question. What we have to do? We have to convert using these vectors. We make one matrix. In that matrix we have to convert into a row echelon form and solve these equations which are made from the row echelon form matrix, and then solution of that, what one theorem states that the null space of A, right, the null space of this matrix is exactly the orthogonal complement of W. That is the one theorem says that. So using we use that theorem here. So the null space of A is the solution space of the homogeneous system Ax is equal to 0, and that is exactly the orthogonal complement of W, right? So now here we have 3 free variables x3, x4 and x5, and using that x3, x4 and x5, and already we have these two equations. First equations is from first row, x1 plus x3 plus 2x4 plus x5 is equal to 0, x1 plus x3 plus 2x4 plus x5 is equal to 0, and then another equation is coming from the second row, that is x2 plus x3 plus x4 plus 2x5 is equal to 0. So x1 is equal to x3, x4, x5. x3 is s, x4 is t, x5 is u. So x1 is equal to minus s minus 2t minus u. When we put the values of x3, x4 and x5 in this equation, first equation, we get the value of x1, that is minus s minus 2t minus u, and x2 is equal to put x3, x4 and x5, the value of x3, x4, x5 in this second equation. So definitely you will get the value of x2, that is x2 is equal to minus s minus t minus 2u. Okay, so that part you can easily solve this one. So we have the value of x1, x2, x3, x4 and x5. So how many basis vector? 3 basis vectors, because of 3 free variables, right? So 3 basis vectors. Here is the solution, x1 to x5. Put all the values of x1, x2, x3, x4, x5. x1 is minus s minus 2t minus u. This is the value of x2, minus s minus t minus 2u. This is the value of x3, x4 and x5, that is s, t, u. Now what is the coefficient of s in this vectors? The coefficient of s is minus 1, minus 1, 1, 0, 0. The coefficient of t is minus 2, minus 1, 0, 1, 0, and the coefficient of u in all these 5 vectors, that is minus 1, 2, minus 2, 0, 0, 1. Hence the vectors minus 1, 1, 0, 0, these 3 are basis vectors, minus 1, 1, 0, 0, minus 2, minus 1, 0, 1, 0, and minus 1, minus 2, 0, 0, 1 form a basis for the null space of A, which is a basis for the orthogonal complement of W. This is not A, this is W, okay, which is a basis for the orthogonal complement of W, right? So Here they complete the solution, and this is quite a good example. This question was asked in 5 marks in this question paper. So next question, question 5a, second part. Sketch the unit circle in an xy coordinate system in R2 using the Euclidean inner product UV, where U is equal to U1 V1 divided by 4 plus U2 V2 divided by 16. This question was asked in 2 marks. U is equal to xy, then norm U is equal to, we know that inner product, square root of inner product U with U, and that is equal to square root of x square by 4 plus y square by 16. So the equation of the unit circle is square root of x square by 4 plus y square by 16, that is equal to 1. On squaring on both the sides, we get x square by 4 plus y square by 16, that is equal to 1. So the graph of this equation is the ellipse shown in the right. Next question, question 5b. Find the least square solution of the linear system Ax is equal to b, given by 2x minus 2y, that is equal to 2, x plus y, that is equal to minus 1, and 3x plus y is equal to 1, right. And also find the orthogonal projection of B on the column space of A. This question was asked in 4 marks. The matrix equation form of the given system of equation. See, A is coming from these 3 equations, where the first row is coming from the first equation, that is 2 minus 2, the coefficient of x and y. Similarly, the second row is from the second equation, that is 1 1, and the third row is coming from the third equation, that is 3 1 xy, that is equal to 2 minus 1 1, 2 minus 1 1. Ax is equal to b, a is equal to 2 minus 2 1 1 3 1, x is xy, and b is equal to 2 minus 1 1. Okay, now Ax is equal to b, so here is one equation, that is definitely we have to find A transpose, we need it. So A transpose is just we have to interchange the row and column. So this matrix A is in form of 3 cross 2, so A